Okay, so I will now present my master dissertation named Design and Fabrication of Farming Greenhouses. So according to McKinsey research, productivity and digitalization of the sector is quite low. And if digitalization is to be improved, productivity can increase up to 15%, while cost reduction can go until 6%. This work was done with collaboration with the company Estufas Minho. It's a Portuguese company specialized in manufacture and installation of greenhouses. The company main goal is to use new technologies to improve productivity in design phases and to automate repetitive tasks. So according to IBM definition of automation is the use of technology to perform tasks where human input is minimized. Modular structures with standardized model allow this kind of optimization. Automated design process can lead to increased productivity, decrease of human errors, time for more value-adding tasks, and increased accuracy and consistency. So to closely understand the case study, first we have to do and explain some theoretical concepts. First one is knowledge-based engineering. Knowledge-based engineering means that we capture engineers' knowledge, organize it first through informal model, which means through interviews and sketches. After that, to structure that knowledge into more formal model like tables, equations, algorithms, and after that to pack it and organize it into computer-based design application. MOCA is methodology for development of these kind of applications. This work is structured into 3 phases. First, we elaborate why are we doing this. Second, we gather and organize the knowledge important for making this case study and to software development. And third one is explanation of software itself. So first, we have to understand the structures that we are trying to produce, and those are greenhouses. Greenhouses are constructions that provide optimal conditions for crop growth by controlling climate elements and providing protection. They should provide high light transmittancy, structural strength, they should be feasible, and they should provide good ventilation and many other factors. So these are modular constructions. Factors that are influencing design are latitude, cultivated crops, building regulations, etc. There are many classifications that can help us to understand these structures, but the most important ones are construction characteristics. So we can understand that there can be many tunnel widths, they can be single or multi-span structures, they can vary in height and roof shape and slope. These are some of the structures that are produced by the company. So we have tunnel greenhouse with vertical walls, and we have Gothic structure. Here we have single span structure and multi-span structure. These are some of the elements that will be later implemented into case studies. So these are capitals that come on the columns that are holding roofs and gutters, and these are clamps that are fixing the elements. So this work was developed within Autodesk Inventor. It's a program that's used as an authoring tool within the company for many years. They possess license for this program, and they made extensive library of models which will be used in case study. What is important to understand is structure of the file. We have part files that are building blocks of Autodesk Inventor. Those are simple models made from 2D sketches and later turned into 3D. More complex models were produced by combining part files into assembly files. So this is the structure of the file. Part files are forming sub-assembly, and part files are forming main assembly. We will be generating main assembly of greenhouse structures. To work and to develop this case study, first we explored how the model is made manually. And it is made with the use of a command within Autodesk Inventor, rectangular pattern. This command is taking the element and multiplying it in the right direction with a defined number of copies and the distances between them. Each element is numerated, and that's going to be important later for the code development. Second concept is module, and it's defined as standardized part or independent unit that can be used to construct a more complex structure. Properties are closely explaining these modules. Since greenhouse structures have many elements and they have many different properties, to structure this kind of knowledge, these kind of tables were developed. So here we explain property name, data type, and values that that property can have. These are the elements that will be included in case studies. So we have outer columns that are different in dimensions from inner columns. We have different kind of roofs, frontal part. We have gutters, capitals, single and double. We have clumps and horizontal profiles. And this is how the modules are seen from in the floor plan and the distances and the repetition between them. To achieve different variations of the model, there are three ways. First one, when the geometry is very complex, like in a roof structure, when we have many elements, and when the arc is not actually arc, but polygonal structure, we directly import some assembly into main assembly. Second thing is when from the main code, we are triggering code within part file that's regulating dimensions. And the third way is through model states. It's newly introduced feature within Inventor where we capture different states of the model. For example, we have two kinds of columns and we capture the thickness 3 and the thickness 2, and then desired state we call with from the main code to come on the right place. So what are we actually doing? We are configuring the product and defining what modules are going into main product based on the user inputs. So if we implement that in our case study here, we have different functionalities, meaning that different options that greenhouse can have. And to define the modules, we have to know what customer has chosen. So to define column, we have to know column height and column section. To define roof structure, we have to know width of the tunnel and type of greenhouse. So our main goal is to automatically generate 3D model based on the inputs of the customer or engineer. And it is done through the code that has three components. First one is Inventor that is used as authoring tool that has iLogic add-in that is used for writing Visual Basic code that communicates with Inventor API. And third component is component folder, which stores all the part files and some assemblies that are used into generating a model. So user, or in this case engineer, puts all the inputs throughout input forms into iLogic that communicates with component folder, taking the right components and storing into model space. And after that, it's producing patterns. So here we have sequence of patterns. How are they being created for one with greenhouse structure? And this is how the program is working. First, we link with the desired component folder, then we input data like column height, width of the tunnel.
Sorry, we cannot hear you properly. Okay, try now.
Okay, it was video and probably connection was getting low.
And please rush because we are out of the time.
Okay, so model was created within a few seconds. When multi-bit greenhouse is created, the code is becoming more complex. So first we create outer columns, and then we create inner columns, and this column is used for the next pattern, and the code can generate different combinations of widths. This is how it looks like, and for this concept, it's only developed on the columns. These are the pattern created, and this is how the program is working. So here we are actually importing different widths of the tunnels. So as a conclusion, use of programming concepts can increase productivity by automating repetitive tasks, and it can also be huge possibility from implementation in other modular constructions. So thank you for attention. If there are any questions, this is my LinkedIn profile.